Okay, welcome to section 1.4, exponential functions. Alright, so exponential functions, we talked a little bit about these in one of the previous sections. So the function f of x equals 2 to the x power is called an exponential function because the variable x is in the exponent. It should not be confused with the power functions. Power functions are when your variable is your base and you have a number in the exponent. In general, the exponential function is a function of the form f of x equals b to the x power, where b is a positive constant. Let's recall what this means. So if x equals n, a positive integer, right? So n is a positive integer, whole number. Then b to the n means simply b times b times b times b times, and we keep going, right? And of course we'll repeat this n times. Okay? Alright, so a little bit of review on exponents here. I'm just going to show you, again, remember I told you in calculus you're going to learn to look at things you've been looking at for years now in math, but see them from a different light. Work with them in a different way. Alright, so b to the negative 3 power, that one should be easy. When you have a negative exponent, it means reciprocal, right? It means flip the fraction. And of course, when you flip it, you change the exponent. You change the sign of the exponent. Alright, next one here, b to the 3 halves. So remember, fraction exponents means radicals, right? So b to the 3 halves power. So there's numerous ways we could write this. Alright, we can write this as b to the 1/2 to the 3rd power. Alright, because the rule here would be multiply the exponents. We could also write this as b to the 3rd power to the 1/2 power. Same thing, right? If you multiply those two exponents, you still get 3 halves. You could also write this as, since b to the 1/2 means radical b, right, to the 3rd power. Another way to write it is radical b to the 3rd. Okay, so just 4 different ways to write the exact same thing. And you'll see as we get through this semester, these different ways are going to come in handy of writing these things. Okay? All right, part C. If we were in class, I would say go ahead and simplify part C as much as you can. But since we're not in class, we'll do it together here. So we can use any of these methods, right? You can use any one you want, whichever is easier. That's usually what you want to do, is whatever's easier, right? Okay, so if you think about this, we're going to say this is 8 to the 1/3 power to the 2nd power, right? But we can realize if we do the 3rd root of 8, which is 8 to the 1/3 power, and square it, this is probably going to be the easier way to do it. Because 3rd root means what number times itself? 3 times gives you 8, and that's 2, right? 3rd root of 8 is easy, so that's 2 to the 2nd power, which is 4. Okay? There we go. Just a quick review on exponents. Let's see. So if x is a rational number, x is p over q, where p and q are integers, and of course q has to be greater than 0, right? We cannot have a 0 in the denominator here. So then b to the x would be b to the p over q power, which, just as I illustrated above, we could rewrite as b to the 1 over q to the p power, or b to the p power to the 1 over q power. Either way, these are all equivalent statements. One reason for the importance of the exponential function lies in the following properties. If x and y are rational numbers, so ratios, then these laws are well known from elementary algebra. These are the things we just went over. It can be proved that they remain true for arbitrary real numbers x and y as well. Okay, so there's all your rules that we just went over, right? Oh no, sorry, these are different rules we did not go over, but these are ones you definitely want to make sure you know. So number 1 here. If we're multiplying same bases, we add exponents. Okay, so if you have the same base being multiplied together, we add those exponents together. That's what they're showing you here. If we divide same bases, we subtract exponents, but in this case, of course, it always has to be top exponent minus bottom exponent. Remember, order matters in division and subtraction. Number 3 is what we were working with above, right? We can switch the x and the y there. It really doesn't actually matter, but b to the x times y power is the same as b to the x in parentheses to the y power. And number 4, sort of like a distribution rule, right? If you have the x outside the parentheses, you've got to make sure you share that x exponent with everything that's multiplied and divided inside the parentheses. Alright, so again, important things to remember. Let's see, so here's an application of the exponential function. The exponential function occurs very frequently in mathematical models of nature and society. Here we indicate briefly how it arises in the description of population growth and radioactive decay. First, we consider a population of bacteria. Suppose that by sampling the population at certain intervals, it is determined that the population doubles every hour. If the number of bacteria at time t is p of t, where t is measured in hours, and the initial population is p of 0 equals 1,000, right, because that would be times 0, that's the beginning. So if we know that it's going to double each time, then p of 0 is the initial. P of 1 means 1 hour later, right, which means double the original population, 2 times the original population, which of course we can rewrite as 2 times 1,000. If we want to see the population at hour 2, we double the previous, right, so double p of 1. Which would be 2 squared times 1,000, right? Okay, we can easily multiply these out, but we want to find a pattern here. What we're trying to find is a general equation for this population model. Alright, so if we want hour 3, we double the previous. But we notice the pattern arising here, right? Third hour, 2 to the third. Second hour, 2 to the second, etc. So by this pattern, we can write a general equation to model this population. P of t, right, so time, how many hours past the original. To get that population, it's 2 to the t times 1,000, or 1,000 parentheses 2 to the t. Be careful though when you write it in this form here. Make sure you're watching out for PEMDAS. If you're going to plug in a value for t, remember, exponents first, find that answer, then multiply by 1,000. Okay? Okay, so the population function is a constant multiple of the exponential function 2 to the t, so it exhibits rapid growth. Under ideal conditions, unlimited space and nutrition, and absence of disease, this exponential growth is typical of what actually occurs in nature. So it just gives you a good idea. Okay. So here's another one. So the half-life of strontium-90 is 25 years. So this means that half of any given quantity of strontium-90 will disintegrate in 25 years. So if a sample of strontium-90 has a initial mass of 24 milligrams, find an expression for the mass m of t that remains after t years. Okay, so we're going to kind of do this same thing we just did in that previous problem. So the initial m of 0, they just told us, was 24 milligrams. Now every 25 years, this mass will be cut in half. So we can figure out 25 years from now, it's going to be 1/2 of the original 24. Okay? And of course, 50 years later, it'll be 1/2 of 1/2 of 1/2 of 24. In other words, 1/2 squared times 24. And we could keep doing this every 25 years, which that's not a problem. So there's a nice little model for you there. But the problem would be, what if you wanted to know the mass in 13 years or 82 years? In other words, a non-multiple of 25. well then this little formula won't help us, right? So what we'd have to do is we're going to say m of t is going to be 1/2 to the t over 25, because that sets up a ratio, right? If you want mass at 13 years, then you want to know what is that mass 13 out of 25 years later, okay? And then times the initial 24. And there you go. Now we could plug in any number we want. For example, part B here. Find the mass after 40 years. All right, so mass at 40 years. 40 is not a multiple of 25. All right, so we would do 1/2 to the 40 over 25 power times that original 24. And again, be careful when you type this into your calculator. Make sure you're observing PEMDAS. Now, if you plug that in to a calculator, you should get, well, we'll see, you'll get something like 7.9 milligrams, but here it says to the nearest milligram, so that would be 8 milligrams. And this is a word problem, so make sure you put units on it. Okay? Alright. Moving on, part C here. Estimate the time required for the mass to be reduced to 5 milligrams. So now we want to find T. So we're going to use that general formula up above, right? So, oops, there we go. M of T equals 1/2 T over 25 power times 24. Okay, so they want us to estimate the time required for the mass to be reduced to 5 milligrams. In other words, M of T is 5. Okay, so some algebra we can do here. Of course, we can divide both sides by 24. Oops. So now we got a little issue here. All right. Our variable t that we want to isolate is stuck in the exponent. So hopefully you remember what to do in this case. What you do is we natural log both sides of the equation. This allows us to use the natural log rules, or logarithm rules as well. One of those rules is nice. It allows us to take this exponent and bring it to the front as multiplication. So we get natural log of 5 over 24 equals t over 25 times, oops, I missed part of it here, times natural log of 1/2. Alright, we want t by itself, so we can divide by natural log of 1/2 and multiply by 25, and that'll clear it, right? So t is, so we have the original natural log of 5 over 24. We're dividing by natural log of 1/2 and multiplying by 25. And there you go. And you can plug this into a calculator. Now be careful, don't do any reducing here. Remember, natural log and logarithms are functions. So do not, repeat, do not say, oh, we can just reduce away the natural logs. You can't do that. Similarly, you cannot reduce these two fractions. You have to leave them as they are. So what you would want to do is kind of think of it like this. Those are parentheses there. Okay, so that's how you're going to enter it into your calculator. If you do that correctly, you should get time equals something like 56.6 years. And again, it's a word problem, so make sure you put units on that. Alright, so don't forget your natural log and logarithm rules. Those are important. Alright, thank you again.